Good afternoon.
Yeah, hi. So today we shall do solve with instructor session for week 9 of machine learning techniques course. Sorry, machine learning foundations course. I hope all of you are familiar now with the contents of week 9. Do you have any general doubts for week 9 before we start the solve with instructor session? Because you need to do some workouts using your calculators and get your calculators be ready with you so that you can solve some matrix manipulations. So let me share my screen. So is the screen visible to all of you? This is a peer deck event. So we are going to do some problems and some calculations so that you can answer the questions using this platform. So there is a link shown in this screen, that is joinpd.com. So kindly go to this website joinpd.com and then type in this code DUFQLU so that you can join this session. So once the students are joined, we can start the SWI session. So let me also paste it in the chat box. So let me wait a couple of more minutes so that all the students join the session. If you have a laptop also, you can join from laptop. Otherwise, if you have mobile phones, also you can join through mobile phone. See, we have more than 50 participants and it looks like only 11 of them have connected to this peer deck. You can give it a try, okay? So in general, in week 9, we have covered optimization basics, and initially sir has taken properties of convex sets and how do you form composition of convex functions and some properties regarding that. And the important part in week 9 is the primal and dual formulation, which leads you to that Kkt conditions. So which is used for solving such optimization problem. So optimization plays a very good part in machine learning in general, because when you study the advanced models or basic models, even in the next upcoming courses, the very basic thing that you need to find a good model is optimization, is only through optimization. Hence in this week 9, we are week 8 and week 9. And in week 7 also I have introduced to optimization. In week 8 and week 9 deals mostly with convex optimizations. So can anyone tell me why do we go with this gradient descent approach for convex optimization problems? We can unmute and talk, right?
It is because the local minima are the global minima in for convex functions, and gradient descent always leads to a local minima.
Yeah, absolutely correct. So thank you for the answer. So yeah, so that is the main reason why we use this gradient descent approach itself for solving this convex optimization problem. Because we are guaranteed to get a local minima, that's why this gradient descent is also guaranteed to reach your global minima, which in turn happens to be your local minima. Okay, so I hope some students have joined. So we shall start the session. So we welcome you all for the Solve with the Instructor session of week 9. So this is your first problem. So which of the following sets are convex, closed, and bounded? So you are given with these 6 functions. The first function A is equal to x comma y, that belongs to this 2D space, that is R2. And the function is x squared plus y squared less than or equal to 4. And the second function is also in a 2D space, which is y is equal to 2x plus 4. And the third function is x plus y less than or equal to 2. And given that x is greater than or equal to 0 and y is greater than or equal to 0. And the fourth function is simply y is greater than x squared. The fifth function is xy greater than 1 and x greater than or equal to 0 and y greater than or equal to 0. And the last function is also the same, where your constraint on x alone is varied with the x less than or equal to 0. Okay, I'm getting some responses. So if you have any visualization tools, if you know such visualization tools, you can quickly visualize this function and then give me the answer. Or, sorry, excuse me. Or else you can also try to draw it in your paper, and then you can also you can have such answer. So if there are any new participants, so this is the website ID, and then to join the session. And below is the code for joining this session. Okay, so I got some good responses. So let's check the responses. Okay, ANC, ABD, ANC, AB, AC, okay, AC. So most of them have got this A as your answer. B, F, A. Okay. Okay. So nice. So almost everyone have got this A as answer, which is one of the correct answers. So still I am receiving responses. Okay. Okay. So we are still receiving responses. So let us wait and then go for the solutions. Okay, so almost all of them I think have responded. So C is also correct, one of the right answers. So there are only two functions which are correct. That is, sorry, A and C. So we can go to the visualization and then verify this answer. Okay. So I hope this screen is visible to all of you.
Yes, it is visible.
Yeah, okay. So your first function is x squared plus y squared is less than or equal to 4, which is obviously a circle. So this circle is a convex function. Why this is a convex function? Because whenever you have 2 points in, say, x1 and x2, the values of f of x1 and f of x2 lies within this circle itself. So if there are any some intermediate cuts, and if it is a non-decreasing function, in such cases, it is going to be not a convex function. So this is a convex function. And we also claim it to be closed and then bounded. So can anyone tell me why it is a closed function?
The range is finite.
Yeah, it is finite, and the boundary points is included within the function itself. That is x squared plus y squared is less than or equal to 4. So which means 4 is also included in this function itself. That is why we call it as closed. And the third option is bounded. So since it is, if you find the finite condition, that the 2 points inside this function is finite. So the first option is absolutely correct. And let us check the second option. So the second option is simply 2x plus 4. So what will 2x plus 4 will be? So it will
Linear.
be a line, a linear line. Yeah. So a linear function is can be either convex or a concave function. So it is not only convex function. Okay. And so let us look at the third function. So the third function is also x plus y less than or equal to 2. And then the conditions are x is greater than or equal to 0 and y is also greater than or equal to. So this triangular part alone is the function's value. Okay. So this is convex function, and also it is closed and bounded. So hence the option A and C are correct. So also let us also check with the other option B. So now a simple function which is y is greater than x squared. So looking at the function itself, we can say that this function is simply a convex function, but what happens to its boundedness and then closedness? Can you comment on it?
It is not closed.
Yeah, correct. So it is, so since this function is open in the upper end, no, so it is not bounded, and then it is also not closed.
Ma'am, why is
That-
option C bounded? It is not. I mean, it's bounded above, but not bounded below.
Yeah, bounded below means that is why this y is greater than or equal to 0. That condition also we have. So this is the axis where your y is greater than or equal to 0. And here it is
Okay.
x greater than 0. So
Oh,
this
okay.
triangular portion alone. Yeah.
Okay.
So since,
Okay.
okay. So there was too much color, so I didn't plot that x greater than 0, since it is understood, right? The first quadrant. Okay. So our fourth function is not convex, but it is not closed and not bounded. So let us look at the other function, the fifth function. So if you see, this xy is greater than 1. So we have two quadrants. So the first quadrant is also the function, and the third quadrant is also the function. But our condition is for x greater than or equal to 0 and y greater than or equal to 0. So that is this quadrant, this function at this position alone. So this is convex function, but it is not closed and it is not bounded. So the last option is xy greater than 1, where x is less than or equal to 0. So here, so this is where your x is less than or equal to 0 and y is also less than or equal to 0. So this is truly not a convex function and also not closed and not bounded. So this exercise is just to let you know that how to visualize such convex functions which are both closed and then bounded. Okay, let's go back to the session.
Ma'am, in this, excuse me, ma'am.
Yeah, tell me.
Ma'am, in the previous question, xy greater than 1. So we have the area above the, in the first quadrant as well as in the third quadrant. So in such
Yeah,
a case,
correct.
if it comes in the exam, should we write it as convex or would it be concave?
So depending on that constraints, you can just write, no, if it is x greater
Okay,
than or equal
so
to 0 and y greater than
y
or equal
greater
to
than,
0.
okay, ma'am.
Yeah.
So in that case, it will be convex.
Yeah, correct.
Okay, ma'am. Yeah, thank you.
Okay. Yeah. Okay. So now the second problem is let f of x is equal to 3 plus x squared plus x and g of x is equal to e power minus x. So what can you say about their composition? That is h1 that is equal to f of g and h2 that is equal to g of f. So these are some visualization questions only. So for your exams and all, such visualization question will not be asked because it is a little bit difficult for you to use some visualization tools while the exam. So that is why I have kept for this solve with instructor session. Okay, I'm getting some responses. So when you say we are going to form a composition, what we do is we substitute the function in terms of the other function. For example, in H1, which is a function of G. So that is F in terms of G. So likewise, you have to substitute the value for X, the function of G. So if you visualize it, do it correctly. And for H2, it is a G of F, which means for G in the place of X, you are going to substitute this F of X function. Okay, receiving some responses. Okay, so let's look at the responses. Okay. 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 So just wait for some 10 seconds to reveal the answer. Okay, so we have received some good responses and almost all of you got the answer is correct, which is the option A. So let us check the visualization. So these are the two functions. Your function f of x is 3 plus x squared plus x, which is represented here. And g of x is e of minus x. So the first function is f of g. So that is the composition. So if you visualize it in terms of that x, we are substituting e power minus x. So the equation turns out to be 3 plus e power minus 2x plus e power minus x. So this is the function, since you can see that. Beautiful. So I hope this applet is visible to you all. So the function h is truly a convex function. And what about the next composition, that is g of f? So can you see this g of f is e power minus 3 plus x squared plus x. So if you zoom in and then if you verify, you can see this function is not a convex function, but it is a concave function. So why I have taken this example is to give you a conclusion that even if two functions are convex, we cannot determine that their composition is also a convex function. That is also one of the property that you have seen in your lecture. So though the functions f and h and g are convex in nature, their composition, if you get it interchanged, it is not going to be a convex function. Okay. So we have also seen one property that your addition of two convex function is always a convex function, right? Similarly, we can some functions, convex functions, when multiplied, also give you resultant as a convex function. See the last option. If you can see here, this is a multiplication of both the functions f and g. So this multiplication is giving you a convex function, but this is also not a guarantee. Not always this holds true. Okay.
Ma'am?
Yeah, we have a question. Do you have any question?
Yeah, if a function. Hello, can you hear me?
Hello? Yeah, I can hear you, but your voice is a little bit breaking. Go ahead.
When is a function said to be concave? If f is a convex function, then minus f is concave. Is that right?
Say, yeah, when the function f is concave and if you have this minus negative of that function, right? That negative of a function is concave function.
Okay. Can't we say that the functions which are not convex is a concave function?
Which one? Functions?
Which are not convex are concave. Can you say like?
Oh, functions that are not convex are concave in nature.
Yeah, ma'am, I'm asking that.
Oh, you're asking. So since there are two functions, right? See, one is a convex function and the other is a concave function. So we also have the semi-convex functions. That property also you would have studied, right? x1 plus x2 by 2. So there may be functions which are semi-convex functions also. So we cannot see that which is not a convex will be a concave. So guaranteed function is a negative of that function is going to be a concave function. That is, we can guaranteedly say. Okay.
How did we say h1 is concave?
This you're asking.
Yeah, ma'am. Yes, the gray line.
So how we are saying that this function is concave in nature? So these curves, see, you have see x1 and x2. So inside a convex function, the points are like, say, if for example, if x1 if I take value as -1, and here if I take the value as -0.5, the function that f of x1 and f of x2, right? That function is always greater than the values of x1 and x2 right here. The property that we studied in
Yes, ma'am.
lectures for
The linear approximation thing.
yeah. So like that only we verify whether it is a convex function or a concave function. The very basic line that we studied in our lectures.
Okay, ma'am. In this case, we can say that it's not convex.
Yeah, correct.
So that we are telling it's a concave function.
That's yeah, correct. That's why I'm telling it to be a concave function.
But like if a function is not convex, that doesn't guarantee that it's a concave.
It is just a negative flip of the convex
Yeah,
of a convex function.
minus
That's
of
why it is convex.
yeah. So if you don't have negative minus of f, how will you define that function to be? You can have like f by 2. That's a scalar multiplication of the function still. So only if you change the sign of a function, the function will entirely change, right? This is similar to that of like how we transform our objective into a minimization and maximization problem. From this only we relate to that conversion of primal and dual functions.
The question was that
Yeah.
if a function is not convex, then it is a concave or not. That's the question. Can we determine concave if a function is concave or not using that the function is not convex?
Okay, that. So for that statement, I think I cannot say it directly because we have seen that only the negative of that function is a concave function. To prove that a function which is not convex is a concave, I think we cannot say like that.
Ma'am, because like if we consider sin x, so it is not convex or not concave.
Something like that, yeah. So even a linear line is either convex and concave. So we can guaranteedly cannot say that if a function is not convex, it is going to be a concave function.
Okay, that was the question.
Yeah.
Do we have any set of rules for concave function as well, like we do in case of convex function?
Set of rules like properties you're asking, right?
Yes, ma'am. Properties that like f of x is always greater greater than equal to the f of x1 plus lambda 1 minus lambda x2. That property.
You can reverse the inequality.
It's just negative.
And
Like
correct.
Like if we put the h1x, if we put a minus sign before the e, we can see that it is like a ball opposite, like it will be down negative. Like if you put the negative sign before the e, you can visualize it. It is just vertically flipped.
Yes, I understand the graph. I can visualize the graph.
Yes, so properties are same. Just it is just like vertically flipped or a negative sign before that.
You can reverse the inequality.
Yes, then if greater than will be negative, less than and less than will be greater than.
Yeah, that is what actually the answer is. See, whatever property you have on this convex function, you just inverse it to get the concave. I hope in lecture also sir has told like that, no?
Yes, yes. It was.
Ma'am, e to the power x and e to the power minus x both are convex, right?
E to the power x and e to the power minus x.
Yes, yes.
Yeah, ma'am.
Yeah, correct.
Both are convex. Yeah. So the minus sign must appear before the function, not the argument.
Yes,
to turn it.
definitely. The whole function, like if a function f is convex, then
f of x is minus f of x. We are not telling f of minus x.
Yeah, yeah.
Yes,
that
yes.
was my query. Yeah. Okay.
Okay, okay. See, that is what I told minus f. It is not like f of minus x. So
Yes,
now
ma'am. I understood.
is your doubt clarified now?
Yes, yes.
Okay. Okay, so there are new participants. So those who have joined new, if you do not have this peer deck website, I'm just pasting it in Zoom chat box. Kindly use that ID and then the code below to join the session. So I have shared it in chat so that you can also join. Okay. So one more problem for visualization, that is, consider the following problem. Maximize the function x plus y subject to the constraints x is greater than or equal to 0 and y is greater than or equal to 0. And minus 3x plus 2y is less than or equal to minus 1. And if x minus y less than or equal to 2. So what you want to verify is the feasible region bounded or unbounded? So for your information, what is a feasible region? So a feasible region for any optimization problem is a common region where all your constraints are satisfied. So that is what we call as a feasible region for the solution for any optimization problem. So you have given these constraints. So if you try to plot these constraints, you will get some common region. Just verify whether that common region is bounded or unbounded. Okay, we have got only 4 responses. So let me give you some couple of minutes to visualize this feasible region. Okay.
Ma'am, the question is the feasible region bounded or unbounded? So we write yes for bounded, is it?
Yes for bounded and no for not bounded. That is unbounded.
Okay.
Okay. So why I had this question is if you had watched my tutorial, you would have come across this feasible region, right? So this feasible region gives us, if it is bounded, only then we can have the optimal solutions. If it is not bounded, we can have more number of values for x and y, but still we cannot go for optimal solution. Okay, I hope we have got some responses. Let us see. Okay, so there are equal number of yes and no. Okay. So let us go for the visualization. So these are constraints, like let us first plot this minus 3x plus 2y, which is less than or equal to minus 1. So the green shaded area right here, this is your first constraint, that is in terms of both x and y. And if you plot the other constraint, that is x minus y less than or equal to 2. So that is this gray region. Okay. So this is the area where your minus 3x plus 2y minus 1 meets, and then this is where your x minus y less than or equal to 2 meets with this region. So now, looking upon this two constraints alone, what you can say this region, feasible region. So we have only this, the line between the C and D. You see, this is the area where it is feasible. So when you add the one more condition, that is x greater than or equal to 0 and y greater than or equal to 0, you can confirm that only this first quadrant here, that alone sounds to be feasible. And that too, what happens here, see, if you try to zoom in also. So this common region here, so that is your feasible region, but this feasible region do not have any bounds here. So it is extending up to infinity. Why? Because this area starts from the 0, 0 here, and then it keeps on diverging, right? So the area keeps on widening, and there are no stopping line here or any constraint over this region to say that the feasible region is bounded. So you can have many points here. So these x and y points that lie in this area, so that is the x value here and y value here that are lying in this area, are candidates for your solution. But we cannot reach any optimal solution. So just remember that when your feasible region is not bounded, you cannot reach at any optimal value for your x and y. There may be many solutions, but we cannot guaranteedly say that it is an optimal value. Okay, so let's go to the next question. So given below is a set of data points and their labels. So this x and y, x is your data points and y is your label. So perform linear regression on this data set. So you are given with the initial value. So let initial w value at first iteration be equal to 1, be 0.1, 0.1. So it is a transpose. So it is a column vector of 0.1 and 0.1. Using the gradient descent update equation with the learning rate of 0.1, compute the value of this weight w at t equal to 2. So we have, so in lecture we have arrived this gradient descent approach for our linear regression problem. So you know the gradient equation. I hope you can simply solve this x and y, do the multiplication, and then just arrive at your gradient value first. And using that gradient value, you find the weight update equation. You have that weight update equation, and then substitute that gradient of this weight. You can get the updated weight value. So this practice may help you to solve such problems in quiz also. So kindly solve it so that you will know the time that you take for solving such numerical problems. So if you have solved it, enter your answer as comma value. Okay. A comma b, like that you enter the value of the first coefficient and the value of the second coefficient. Okay, we have got one response. Others also, please try this numerical example.
Ma'am, it's heavy on calculation, so some time.
Okay, I will give you some time.
Yeah.
You can guess this time taken no, during the exam also. How much time do you need for such problems? Okay, so we have received 5 responses. Shall we see the solution? Or, do you need still more time to work on this problem? Okay, so let's proceed. So 2 of the students have got the answer is correct. So this is the answer, that is 3.64 and 4.8. So shall we work out this problem so that everybody try to get the correct solution, or it's easy for you to just do the matrix multiplication?
I think we can solve.
Okay, can solve, right?
Yes, it's easy.
Yeah, so this is not, I didn't ask for any such more iteration, just a single iteration. So you have the value for x, so that x is the value of c, for example. So can you see the screen? Okay. So we have this x and y given to you. So this x transpose. So x is a matrix of 1, 2, 2, 1.5, 2, 3, and 3, 4. So that is, so your x should be 1, 2, 2, 1.5, and 2, 3, 3, and 4. So this is your X matrix, that is a data point matrix, and Y is the matrix of a column vector with 2.5, 3, 5, and 7. So once you have this X value, just find this equation using this gradient equation.
Hello,
So
ma'am.
X transpose X into W. Yes.
Here in the gradient equation, the x transpose x into w, the w will be wt or only the w1 always. I mean for each iteration.
Yeah, for first
In the,
iteration. So
no, in the gradient equation.
in the gradient equation, for the first time you computing, right? When this at time step 1, at the first time step, you use this initial value. So that is why I have not explicitly mentioned this W1 here. This is a general equation. So once in the initial step, you are given with this value for W, right? So you substitute that W here. And when you move for other iterations, you substitute the updated W value. Initially, you substitute this value.
So for each iteration, we have to like calculate the grad f every time, right?
Yeah, every time. Because this, once you have computed this X transpose X value, no, this will remain the same because there is no changes for this data points value. And this value X transpose Y will also be the same. So only for the first time, if you compute it, you can keep those values. And this W alone for every iteration, we update with the previous iteration value.
Okay.
I have one doubt regarding this, ma'am. Hello.
Yeah, tell me. Hello?
Yeah. So, see, sir had given this formula that Wt plus 1 for the gradient descent. Wt plus 1 is equal to Wt minus eta t and the gradient of Wt, right? Hello.
Yeah, correct. Tell me what is
Yeah. So now my doubt is, when you're saying calculate W at t equal to 2,
Yes.
that means I have to, if I take the formula it given, that means Wt plus 1 means I have to calculate W3. So that means there will be 2 iterations. But this calculation actually stops after the first iteration.
Yeah, correct. So this is your weight update one, right?
So this, okay, so we are saying,
Let me come to that update equation. So I hope everyone have got this matrix value for x transpose x. You can verify with the solution. And then once you found x transpose x, you are going to find this x transpose y. And you have this solution. I hope everyone would have actually get this solution for x transpose y.
I've got.
Okay. And then you are substituting this x transpose x and x transpose y in this equation along with this ws point on point one to get this value, right?
Yeah. Now here my doubt is here only.
Yeah.
You put W2 is equal to W1 minus eta gradient of W, right?
Correct.
Now the formula what sir has said is W is T plus 1. Now T you're given as 2. If you
Second
go to the
iteration.
question, no, if you go to the question,
okay,
the T is given equal to 2.
Correct.
So if the formula says WT plus 1, then
oh, you're asking like, okay, fine. Then okay, I understood what your confusion is.
Because
sorry for that. Okay,
even in that in the grade, I think this was question in the graded or I don't know where, even there I did one extra iteration. So I got confused why, because the formula says T plus 1.
Yeah,
WT.
so then for that, no, you should have understood that the T is equal to 1, no, initially.
Right, because the options were given, it was correct, but I just got confused.
Okay, see here, when I'm given as T is equal to 1, your T plus 1 will be equal to W2, right?
Right. But in the question you mentioned T equal to 2.
Okay. At that time you got confused. I understand.
Ma'am, it will be better to state the number of iterations that we have to compute. That will be much easier.
So instead of this T equal to 2, maybe if we have given like for the second iteration. You're mentioning that, right?
Yes. Then it's clear.
Yeah, that will be clearer. Yeah.
Okay. See, when T equal to 2, no. So what it is, your iteration does not start from 0. So when you get 0, 1 and 2, at that time you will have 3 iterations. So since we have given like T equal to 1, so I thought it is understood that this is the first iteration and this is the second iteration. That's it. Okay. So we'll avoid such errors in the quiz also.
Right. Thank you.
Okay. Thank you for the clarification too. So once you have obtained your gradient value at first iteration, use this update rule to find the gradient value for the second iteration. So you are given with a learning rate 0.1. So substitute this eta as 0.1 and then this gradient value and then previous weight value to get the updated weight value. So this is your updated weight value. Okay. So I hope everyone is clear with this calculation. Let's move on to the next question. Okay. So given below is the primal form of the linear programming problem. So which is maximize 3x1 plus 5x2 plus 9x3 subject to x1 plus x2 plus 2x3 less than or equal to 6. That is your first constraint. And 2x1 plus 3x2 plus x3 less than or equal to 8. And these are the two constraints. And the variables are x1, x2, x3 are greater than or equal to 0. So what is the question here? The dual objective problem has how many variables? So when you convert your primal to dual problem, you will do some conversions and changes between the constraints and variables. So that to clear that concept, I've asked this question. Okay, we are getting responses. So let me give you some 1 minute just to think on how many variables that you will get for this dual problem. Okay, I received some responses. Okay, let us check the answer. Okay, 2. Okay, still counting. Okay. So 7 of you have got the correct answer. The answer is 2. Sorry. So why the answer is 2? Because if you look at the question had 2 constraints. So for the dual problem, the number of variables is equal to the number of constraints given in your primal problem. So that is the answer. So you had the objective function with 3 variables, x1, x2, x3, and 2 constraints on those variables, which is given in the previous question. So your dual variables are 2, that is equal to y1 and y2 based on the number of constraints. Okay.
Excuse me, ma'am. I have a question.
Yeah, tell me.
Yeah, why don't the positivity conditions on x1, x2, x3 do not count as constraints? Like
While solving, yeah, correct. So this question now last term also we had. So why in the sense these are the variables of your objective function. Okay. So what happens is when you implement such Lagrange multipliers for this x1, x2, x3 alone. So at that time, anyhow, at the final stage, you will get your dual variable also greater than or equal to 0. So what is the value that is imposed on these variables will definitely be imposed on this dual variables also.
okay,
So
so
that is
ma'am,
why
they
we
are
don't take that into consideration as main constraint because
okay,
they're not.
ma'am. Yeah.
Yeah, just a second.
Yeah.
Let me finish.
Okay. Okay.
So this x1, x2, x3. So these are independently the constraint on that variable alone, right? So they
Yeah.
are not influencing any combination of the other variables. It's only that
Okay.
particular variable alone.
So are they dependent constraints, like redundant constraints?
Redundant constraints, I mean, we cannot say that redundant constraints because we may use that for checking this optimal solution. It is
Okay,
used
so
for checking
okay.
the optimal solution.
Okay, ma'am, if there are redundant constraints, like we say that we want to find solutions above a particular plane. Suppose the plane x3 equals to 10. That is x3 greater than equal to 10. Okay. And another condition we say that x3 greater equal to 8. So these two conditions are together, we can just combine them to be just x3 greater than 10 only. So in that case, do we are there any concept of such redundant constraints, like we can reduce the number of constraints if they are dependent on each other?
So far I have not come across such redundant constraints concept, so I cannot comment on it directly. So if you can you start a post in Discord so that I will also look into such redundant constraints and concept, and then I'll answer you that. Is that okay? Truly speaking, I have not used such redundancy concepts. This we can see that in features, no? When you do such, for example, PCA and all, we go for reduction of features.
Yes.
This optimization is also similar. Like, see, if you have more number of variables, that means there are more number of features. Like x1, x2, x3 is corresponding to the variables of the function.
Yes.
So there may be redundant variables. I also agree to that point, but I don't know whether the constraints that based on such redundancy we can reduce or not.
So, ma'am, in this question, if we add a new constraint, a third constraint, 3x1 plus 4x2 plus 3x3 less than or equal to 14.
Okay.
So that's basically addition of constant 1 and constant 2.
Okay,
These
so
constants,
you're claiming to be that redundancy constraint, right?
yeah, because the third constant is essentially a linear combination of the constant 1 and 2.
First and 1 and 2.
And it does not reduce the feasible space in any way. It's really, really, so on primal
correct.
when you see, you would be tempted to answer it is really 3 because there are 3 constants, but really it's uniquely 2, not 3, because the constant 3 is a linear combination of 1 and 2. So this is an example of a constraint which is redundant. It adds no value.
Yeah, correct. So I understand the concept of redundant constraint, but I cannot say that whether mathematically that we are neglecting such redundant constraints or not, while converting it into a dual problem. So that is what my doubt is. My doubt is, I agree that we have that redundancy in the constraints. So when we are converting it into a dual problem, we have to change the objective function also for the dual based on these constraints. So that's why I just need some, I don't have mathematical proof for accepting that answer. That is why I asked him to start a post and discuss. I will also verify whether we can remove such redundant constraints or not. Okay, so let's move on to the other next question. So here we have a primal objective function of LP problem, that is minimize 20x1 plus 40x2 subject to this 3 constraints. So enter the dual objective function. Just for this question, you also convert this primal problem into a dual problem. The next question is I'm asking you to type the constraints. So if you do it completely, it will be useful. Just convert this objective function also, and then the constraints also. For this question, just enter the dual objective function. So I'll give you time for a couple of minutes, 2 more minutes. Just try to solve this conversion. How do you provide the variables, dual variables? For example, consider y1 as your dual variable. Y for the dual variable notation. So accordingly, assign y values and then find the objective function. Okay, we have 5 responses totally. So let me give you 1 more minute. So try to post your responses. Okay, let's check the responses given by you. Maxima is 108y1 plus 36y2 plus 100y3. Okay. So your objective function is correct. So let us look at the next question and then I will finally show the solution. So this is the next question where you typed your constraints equation for this question. Okay. So once you have given responses for this constraint also, then I will show you how to work out this conversion. Okay, we have got some responses. Let us check the answers. Okay. The first one is correct. Yeah, almost all the answers are correct. Okay. Yeah, so that's the solution. See, so I hope I have got it correct. So let me solve it. So when you have this primal problem, for bringing the dual solution. So the dual objective function is primarily you convert this minimization to a maximization problem. So that is the first step that we do. We maximize the function. And then we assign the variables for the constraints. So that is for this constraint, you assign the y1. For this, you assign y2. For this, you assign y3. And based on the value of this equation, you bring it to the objective function. For example, see how do you convert this objective function? So the objective function is 36. So you're going to maximize the function like here. See, this is the value 108, 36, and 100. So 108 y1 plus 36 y2 plus 100 y3. So that is your objective function of the dual problem. And then the constraints are subject to. So here you are going to form the first coefficient. That is for x1, we have the coefficients, right? 36, 3, and 20. And for the x2, the coefficients are 6, 12, and 10. So therefore, 36 y1 plus 3 y2 plus 20 y3, and then the value for coefficient x1 is 20 here, right? So we write it as the inequality symbol is here greater than or equal to, so we write a less than or equal to 20. Hope I am doing it correct. And then similarly, the second constraint is 6y1 plus 12y2 plus 10y3, which is less than or equal to 40. Okay.
Ma'am, but we have to change the equality symbol now.
Yeah, so the greater than or equal to symbol is less than or equal to, we have to write, right?
Yeah, ma'am, but
Ma'am,
in the
Yeah.
the same question
Third
that
equation.
if the primal, if the question was given like the dual one, then both the inequality are less than equal to. Then if I have to change it to the primal one, then I maybe put all the equations in greater than equal.
Yeah, you have to change the inequality sign.
No,
Here
okay,
inequality.
can you open the whiteboard?
Do you want to
What you
open?
have, yes, ma'am, what you have written
Okay.
here,
What
ma'am.
you're
You
asking?
see, yes, ma'am. The less than equal 20 and less than equal 40. From here, if I have to reverse back, then I would have put all the inequalities
This one.
like x1, x2, yes,
And
as
then you
greater than
convert
equal.
it to greater than or equal to.
Yes, ma'am. But the last equation 20x1 plus 10x2, that is less than equal 100. Then how can I know that which one is greater than which one is less than?
So this one you're asking, right? Why this is less than or equal to?
Yes, ma'am. Yes, ma'am.
How do you transfer it back?
Yes, ma'am. Like if this is in the exam question, then I definitely will write the greater than equal. So how can I know that?
Here you are asking that the constraints are like that. Okay, okay. So I hope then we can uniformly change all the values to minus 20x1, minus 10x2, which is less than or equal to minus 100. Is that okay? So
Okay,
now
okay, okay.
change this constraint equation uniformly to the same equation. Sorry,
So
greater
all
than.
the signs would be same.
All the inequalities, if you keep it to be same, at that time, if you convert it, that will be, I think, a bit more confusion free.
Okay,
So
okay,
at
got
that
it,
time,
got it.
get the confusion. Yeah.
but the
Yes.
objective function will change, no, ma'am.
No, no,
Yes,
you
ma'am.
are multiplying this whole equation, whole constraint by negative, no?
No,
But
ma'am,
the
the question is,
dual constraints will change, right? In this case, it will become minus 20y3.
Yeah, that is
ma'am,
what I'm
I think the
going.
question is, if the dual is given, how will we identify if it is greater than or less than, if we are moving from dual to primal? So how will we understand that the third constant will be less than or greater than?
Yeah, just a
If we go
second.
in the reverse way.
So in this problem, instead of this negative sign, you replace with the negative. So that is what you do, right? So since I'm reversing this inequality, I'm also giving this coefficients also negative sign. I hope this is what you're claiming.
Yes, ma'am. That is what you're asking. The negative
Okay.
sign.
Okay, fine. And here also you do it with the negative sign instead of this.
So should we follow this method actually?
Yeah, I think it's easy to use when all the inequalities are same.
Okay.
Yeah, I hope this looks better, correct, I think. Because when I solve this Kkt condition problem also, at that time what I do is I convert this inequality into a less than or equal to, sorry, this greater than or equal to inequality.
Right, ma'am. I have one more question.
Yeah.
If one of the constraint is greater than and the other two are less than, then which, and it's a minimize, then which one should we change?
Oh, which one to change in the sense, which one you are going to?
Yeah,
which one
change
to
the
pick basically? Should it be
which,
greater
yeah.
than or
Correct,
less
correct.
than?
Yeah.
Correct, correct. See, initially I too had this doubts while solving such optimization problems. Okay. So sometimes what they do is uniformly, if you do that conversion, that is okay. If you do it for one, for example, if I'm converting this less than or equal to all the other constraints,
Okay.
you
Got
should
it.
not leave anyone. Yeah.
Right.
If you
Got it.
apply any sign change, do it uniformly to all the constraints, and then it will reflect to your objective function.
Ma'am, there's no particular rule, right? If there is minimize, you have to do a greater than or equal to.
It is based purely on our application only. It is not. We do not have any such rules.
Okay. Okay.
Yeah. Because we cannot impose such condition for the constraints, right? Because we want some function is there. We want to find its minimal value, or we are going to find its maximal value. So the constraints may be like anything based on our application.
Okay, ma'am. And similarly, ma'am, when we put y1, y2, and y3, will it all be greater than 0 for this maximization problem?
We cannot guarantee that also, right? That greater than or equal to. Here, this variable only you're asking, right?
Yeah, ma'am, when I convert it to dual problem and I make it into a maximization, again, would that be less than? Because I get confused whether it would be less than or greater than.
Based on this minimization or maximization, this x1, x2 variable that given is around the same. No need
Given
to
is same,
change
ma'am.
them.
When I convert it into a dual and I have new variables.
Yeah, that only I'm telling. So even when this y1 only asking, right? So here your y1 is greater than or equal to 0 and y2 is greater than or equal to 0, and that does not change usually based on this minimization or maximization.
Okay.
Yeah.
Those are two. Those things are for keeping the graph in the first quadrant, right?
You are telling for the first quadrant alone.
Yes.
That is just for considering this convex optimization problem. We do not deal with the concave optimization, right? When you go for dual problem, which is maximizing.
I am asking that the x1 greater than equal 0, x2 greater than equal 0. Is that for keeping the problem in the first quadrant?
In the first quadrant, correct.
Okay.
In this problem, it is like that. You're correct. Yeah. So one more question we have in chat box. See, initially I have considered this less than or equal to equation. So now what I did is I have changed this constraint to be uniform with the other two constraints. So therefore this coefficient value here changed to negative sign. So that is why we have written this minus 100/3. Okay. So this is the solution for this question. So now, okay. So the last question for the session is.
But the solution is wrong, no, ma'am, because now we'll have to change the signs.
Yeah, we have to change the signs. I will change it and I will update in the portal.
Right.
Thanks for the clarification too. So, using this Kkt conditions, try to solve this linear problem. So your function is f of x is equal to 2 into x1 plus x1 the whole square plus 2 into x2 minus 4 the whole square, subject to two constraints only, x1 square plus x2 square less than or equal to 9 and x1 plus x2 greater than or equal to 2. So when you come across such Kkt condition question, the first thing that you do is you try to fix the constraints for this minimization problem. For example, in our lecture series, sir has taught us that when you want to minimize a function, the constraint g h1 of x is less than or equal to 0. That constraint we have studied in the lecture. No? So what I prefer is you retain that x1 square plus x2 square less than or equal to 9 constraint as it is, and then change the second constraint, which is x1 plus x2 greater than or equal to 2, and then reverse it to minus x1 minus x2 less than or equal to minus 2. Because there are two different constraints with two different inequalities. So we have to have a same inequality for solving this optimization problem.
Also, ma'am, it should be always less than or equal to 0. So we bring the 9 on the left hand side, right? Generally 9 and 2.
9 and 2, we can bring it to the left hand side.
Left hand side.
Yeah. So let me show you this Kkt condition. So I hope you all have come across this practice assignment solutions in the live session that happened earlier. Excuse me. So we have 4 Kkt conditions. One is the stationarity condition. And another one is that complementary slackness condition and primal feasibility condition. And then dual feasibility condition. So I'll give you a shortcut method to do this problem. Yeah. So these are our 4 constraints. So you can refer to this slide for the equations. I'll show you the way so that you can just do it easily. So you have the function f of x. So first thing is you find this stationarity condition equations. So for that, you first obtain the gradient of this function f with respect to x1 and x2. So you compute this del of f of x. You will get 2 values. And then once you do that, you have this to be g1 of x. And this equation, please convert to minus x1 minus x2 less than or equal to minus 2. So that is going to be your g2 of x. Okay. So once you find this del of f of x, find this del of g1 of x and then del of g2 of x. Okay. So once you have obtained these three gradient equations, you can simply get this stationarity conditions. And then ui's are your Lagrange variables. So you have 2 functions. So for g1, you assign u1. And for g2, you assign the Lagrange variable u2. And one thing, before solving the set of stationarity conditions and complementary conditions, you have the table like this. For this u1 and u2. So you first consider u1 equal to 0 and u2 equal to 0. And you consider u1 not equal to 0 and u2 not equal to 0. So this is the easy method for solving your Kkt conditions. So when you substitute this u1 equal to 0 and u2 equal to 0, at that time you can find your x1 and x2 and u1, u2 values. u1, u2 are 0, okay. And the second case is u1 equal to 0 and u2 is not equal to 0. At that time you solve and then try to find x1, x2. Similarly, you do for the other 2 cases. Only for one particular case, you can satisfy all the 2 primal feasibility and dual feasibility conditions. So this is your complementary slackness and this is your primal feasibility and this is your dual feasibility.
Can you just explain this box again, ma'am? You were saying this u1, u2. I missed it. I was working on the problem.
Oh, okay, sorry.
Yeah.
See, when you arise, so have you got this stationarity condition?
Yes, that's clear.
Okay.
I got it. Yeah.
Okay, so and then you would have got this complementary slackness condition as well.
Right.
So we use only this stationarity condition and complementary slackness conditions for solving these 4 variable values. Okay. We use this primal feasibility and dual feasibility for checking whether our answers are correct or not. So the first step you may use to solve is you substitute u1 equal to 0 and u2 equal to 0.
Okay.
So these 2 values, if it is equal to 0, what it means, See, we have this slackness condition, that is U1 into G1 equal to 0. So
Right.
when I say U1 equal to 0, automatically it means G1 is not equal to 0, correct? So this G1 will exist, right? G1 should
Right.
be equal to 0, right?
Right.
So at that time, you can neglect some equations and then you can directly work upon the value for x1 and x2.
Okay.
Yeah. Similarly, you have this U1 equal to 0 and U2 not equal to 0 condition. So
Right.
at that time, since U1
Okay.
is equal to 0, yeah.
Yes.
So you can proceed
Yes.
easily without any divergence in the values. Because if you follow this step, no need to worry about two values for x1 and x2 or how to will I substitute which value for which equation and all. So
Okay.
those can be avoided. There's
Right.
only 4 cases are there. Yeah.
Can you please solve this? Like,
Yeah, sure, I can solve it.
yeah.
Let me see whether anyone have responded. Okay, waiting for response. Okay. Okay, let me do the initial step of solving so that let you all also try to solve this equation. Okay. So now, so let us start with the del f of x value. So have you got this gradient value? So I'm going to derive this function, partially derive this, differentiate this function with respect to x1. So at that time you'll get 4 into, so 2x1 plus 1, this term alone contains x1, right? So you expand this equation, you will get 2x1 square plus 2 plus 4x1, right? Should I write this? For this alone I will write, you just verify. So 2x1 square plus 2 plus 4x1. So this is the expansion, right, for this first term. And for the second term, it is 2x2 square plus 32 minus 16x2. So for your gradient function, the first term is partial derivative with respect to x1. So here the terms with x1 is 2x1 square. So when you differentiate, you will get 4x1. And here you have another x1 term. So that is 4x1 plus 4. Others are equal to 0, right? And the second term is you are differentiating with respect to x2. So here the term is 2x2 square. Therefore, I get 4x2 and minus 16x2 is there. So minus 16. Okay, so this is their gradient with respect to f of x. So now we go for gradient with respect to g1 of x. So that is very straightforward. So your g1 of x is simply x1 square plus x2 square. Let us not worry about the constant term, which is going to be equal to 0. So at that time, your first term is with respect to x1. Therefore, it is simply 2 into x1. And the second term with respect to x2. Therefore, that is also 2 into x2. Okay. So your second constraint is g2 of x. So g2 of x is minus x1 minus x2. That is your g2 function. So differentiating with respect to x1, you will get minus 1. And with respect to x2, you will get another minus 1. So now we have arrived at our gradient equations. Now we write in the stationarity condition. So the first condition is we have this, so you can substitute and then write, or else you can directly write this first term. So your first equation is with the first row. So 4x1 plus 4, and you have to multiply u1 into del g1. So plus u1 into 2x1. And the second term is here minus 1. So you are going to apply u2 into this g2. So plus u2 into simple minus 1. So that is equal to 0. So that is your first stationarity condition. So here, what about this one? This is the another inequality, right? That is how we derive this stationarity condition. So let's not worry about this Vj variable here, Vj multiplier. Let us work only with the Uj multiplier. So now for the second stationarity equation,
I'm sorry to interrupt, ma'am. Ma'am, that Vj comes when there is an equality condition, right?
Equality condition, correct.
Yeah. Okay, ma'am. Otherwise, we don't take that at all if it is not there.
Yeah, otherwise no need. So if your constraints have that one, you can use. Otherwise, no need to use.
Okay, ma'am.
Yeah. So now the second row is 4x2 minus 16. So similarly have this u1 multiplied by 2x2 and plus u2 multiplied by minus 1. So that is equal to 0. So I have this as equation 1 and then this as equation 2. And now you write this complementary slackness equation. So that is easy, right? So u1 into this g1, which is u1 into, for now you have this 9 here, right? So now what you do is, when you write this function, some multiplication, you write g1 square plus g2 square. You are bringing this 9 to left hand side, therefore minus 9 is equal to 0. And for the second equation here, you are applying u2. So u2 into x1, minus x1 minus x2 plus 2 is equal to 0. So these are the 4 very basic equations. You can have the other equation as the constraint itself. So this is the primal feasibility constraint. So this is your equation 5 and this is your equation 6. And your dual feasibility condition tells us that u1 should be greater than or equal to 0 and u2 should be greater than or equal to 0. So this have it as 5 and have it as 6. Sorry, 7 and then have it as 8. Okay. So once you frame this set of equations, you can now apply these 4 cases here. So the first case tells you u1 equal to 0 and u2 equal to 0. See what happens here. So when so it will take time, I think so. So is my is the screen visible till the end, or should I increase my handwriting?
It's visible.
Okay. u1 equal to 0 and u2 equal to 0. So at that time, what will happen here? See, here also you have u1 equal to 0 and u2 equal to 0. You substitute in this equation 1 and 2. So our main objective here is, see, substituting the value for this Lagrange multiplier is easy, okay, because we cannot say that this x1 and x2. Why I am doing this? Can anyone relate to that? Why I am taking this condition? Because of this dual feasibility condition, because this u1 should be greater than or equal to 0. So it is either equal to 0 or it is greater than 0. So that is why this condition helps us to easily come to the optimal solution. Okay. So substituting u1 equal to 0 and u2 equal to 0 here, this term will vanish and this term will also vanish. What you will get? 4x1 plus 4 is equal to 0. So what is your x1? x1 is equal to minus 1. Can you get my point? And when in the second equation, you are going to substitute u1 equal to 0 and u2 equal to 0. So these two terms are equal to 0, they will vanish. And once again, we are left with 4x2 minus 16 is equal to 0. So here x2 is equal to 4. So now you have obtained this x1 and x2 and you have your value for u1 and u2. So u1 and u2 is of course satisfying our dual feasibility. So can you verify this x1 equal to minus 1 and x2 equal to 4 satisfies this primal feasibility or not? Can you work and tell me whether it satisfies these two conditions?
Not the second one.
Minus 1, 4. Yeah. So this is minus 1, 4. That is for your x1 and x2.
Ma'am, if suppose it satisfies and we don't work out the others, can we say it is an optimum solution? We can't, right?
I mean, it is supposed to be the optimal solution. Maybe for if you want to check with the others, you can verify, because for no other value you may get the optimal
But
solution.
suppose if there is other x1, x2 for which again we get an fx which is minimum. I mean, is that
Maybe
possible?
So far I have tried, I have not get such conditions. I have worked with some this kind of questions.
Yeah,
If you
because if
use
the
these,
first shot I am getting the constraint as true, and if suppose I don't go ahead, will that be okay? Because that saves time during exams. That's the reason I asked you that question, ma'am.
yeah, okay, fine. See, actually, this works very well. No, I have tried for many problems, and this condition, these 4 cases will definitely give you the only one optimal solution.
Okay, ma'am.
Yeah.
So the first one we approach, we get it, and we stop the working, right, ma'am?
Yeah.
Okay.
Yeah. So in that case, if you want to do, you have to start from this side of the box. That is with u1 not equal to 0 and u2 not equal to 0.
Okay.
Because maximum at times what happens is when this u1 and u2 are equal to 0, at this time the optimal solution is not obtained in many cases which I have built so far. Either
Okay,
one of them will be positive. You will get some value for the Lagrange multiplier because that gives you how this constraint is working.
Okay, okay, ma'am.
So if you start from here and then if you approach the problem, then you can definitely, you are sure to get the answer.
Okay. Thank you, ma'am.
So now if we have verified that for u1 and u2 equal to 0, these 2 conditions are not satisfied, right?
Right, ma'am.
1 squared plus 4 squared, which is greater than or equal to 9, and it's not equal, not less than. So this cannot be the optimal solution. So similarly, you have to try for these 3 cases. So now as said, we can also, so can you try and give me the solution for this just one case? So that is the case 4, because that is where your answer is. u1 is not equal to 0 and sorry. u2 is not equal to 0. So now since we are out of time, we can just solve one other case, that is u1 not equal to 0 and u2 not equal to 0, and see how we arrive at the solution. Okay. So now what happens, see when u1 is not equal to 0, automatically from the complementary slackness, you can write that this term x1 squared plus x2 squared minus 9 is equal to 0 from this equation 3. So from this equation 3 and 4, that is from complementary slackness equations, we can write that x1 square plus x2 square minus 9 is equal to 0. Why it is equal to 0? Because u1 is not equal to 0. We cannot say that value of u1. Because in lecture also, sir clearly mentioned that your complementary slackness tells that either this u1 is 0 or this g1 is 0. So that is what our condition is. So that is helpful for us to solve this problem. So similarly, u2 is not equal to 0, which means the second term x1 minus x2 plus 2 is equal to 0. So from here you can write from this equation, this x1 is equal to x2 minus 2. So we have x1 in terms of x2, substitute here in this equation, you will get x2 minus 2 the whole square plus x2 square minus 9 equal to 0. So can you solve this equation and then tell me the answer for this reduced form?
Ma'am, there is small correction, like it was minus x1.
Yeah, which one? Oh, here, sorry. Yeah, thank you so much. So your x1 is equal to 2 minus?
x2 minus 2.
x2 minus 2 minus x2, right?
Yeah, 2 minus.
Okay, great. So 2 minus x2 the whole square. So what is this equation now? You expand this square term. So you will get 2x2 square minus 4x2 minus 5 equal to 0. So this is a simple quadratic equation for which the solution you can simply arrive by having this solution of this quadratic form, you know, no, right? Minus b plus or minus square root of b squared minus 4ac by 2a. So you can solve that one. No? And then can you tell me the answer for x2 value? It will take just a minute or so, so that it will be easy for us to proceed further. Tell me the value for this x2 from this quadratic equation. So anyone calculated the answer for x2?
Ma'am, 2.
Yeah.
2 plus minus root 14 by 2.
Okay, so 2 plus or minus?
Root 14 by 2. Root 14?
Root of 14.
Yes, ma'am.
But, okay, root 14 by 2. Okay, so can you just use a calculator and then if you verify this?
2.8, comma 0.8.
Correct.
Minus 0.8.
Okay, fine. So 2.8, comma minus 0. So to be precise, you can use 2.87, comma minus 0.87. So we have obtained this x2 value. So using this x2 value, you substitute in this equation for getting this x1. So that is very easy, right? So x1 is 2 minus x2. So 2 minus 2.87. So therefore minus 0.87, comma. So 2 minus of minus 87, therefore 2.87. Okay. So these are the values for x1 and x2. So for x1 we have 2 values and x2 we have 2 values. So for these combination we have to find this u1 and u2. Okay.
U1 and U2 finding may not be required, right? We just need to substitute this in those equations and find if it is okay or not. Is that required to find U1 and U2?
And that is actually one of the approach, because when you want to verify whether this dual feasibility condition, at that time this U1 value is not known to us. We are just assuming that U1 is not equal to 0.
Okay, okay.
It is not on any sign restriction, right? So it may be minus or it may be plus.
Yeah, right.
Yeah. At that time, we have to choose which value for x1 and x2 corresponds to the optimal solution. Right now, we have 2 different choices. Okay. So for solving this equation, from this 1 and 2 equation, you substitute the value for x1 and x2 here. So we know that x1 and x2. So let us consider the first option. Let x1 is equal to minus 0.87. And one more thing you can notice is why we are using this negative also, because in the optimization problem, we did not give any restriction for this x1 and x2 sign. It is only with respect to some constraints alone. If there it is written like x1 is greater than or equal to 0, at that time you can directly consider only one value for x1. So now let us consider x1 equal to minus 0.87 and x2 equal to 2.87. So from the equation 1 and 2.
In the question, you have not given x1 and x2 is greater than equal to 0.
I think I have not given, only I'm just written this subjective function and subject
Okay,
these
yeah.
two values.
Right. Okay, thank you.
Okay, yeah.
But ma'am, in
So
such a
this-
case, ma'am, if suppose x1 and x2 are greater than or equal to 0, but because this pair comes out to be 2.87 and minus 0.87, so this kind of answers.
This value, this case will not work. You have to go with another case. You can directly neglect this case and then you can skip to the other case.
Okay, ma'am.
So now, since this from this 1 and 2 equation, you just simply subtract this second equation from the first equation, because at that time you can cancel this u2 here and you are left only with u1, so that you can easily find the solution for u1. So let me write that solution alone. See, from what you do is 1 minus 2. So at that time you will get 4x1. I'll write the first equation. You just complete the question. Okay? Give me the answer. 4x1 plus 4 plus 2 u1 x1 minus 4x2 plus 16 minus 2 u1 x2 is equal to 0. Our u2 will get cancelled. Okay? So if you write this is what I have written. So 4x1 plus 4 plus 2 u1 x1, these two and all becomes negative, so it's cancelled each other. And then minus 4x2 minus plus 16 plus 2 u1 x2. Okay. So can you substitute the value for x1 here from this equation and try to reduce this equation and give me the value for u1. u1 equal. Just a simple steps of calculation. Try to group the elements x1 wise and then try to just substitute the value for this x1 x2 so that you can directly get the value for u1.
Ma'am, you get it as 0.673, 674.
Correct, perfect. So u1 is equal to 0.67. That is the correct answer. So did any other of you also try this value? So this is the value for u1. So now you have known this u1 value. So what we can do is you can substitute u1 in the second equation and find this u2 value. That is also simple, right? So now substituting this value in 2. So that equation is u2 is equal to now 4x2 minus x2 plus 2 u1 x2. So substitute value for x2 and u1 here so that you can get this u2 value. So the same equation here. 4x2 minus 16 plus 2 into u1 into 2x2 is equal to this u2. So since it is negative, you can directly take it to this side. u1 into 2x2. Okay, fine. So what is the value for this U2?
Ma'am, it comes out to a minus 0.67. Ma'am, is it 4x2 or 4x1?
What I have written?
Ma'am, actually I
Yeah.
got U1 equal to 0.78 and U2 equal to 0.448.
What is your value? U1 equal to?
0.78
Okay.
and U2 is 0.448.
Oh. But I get some different answers. Okay, let me cross check once. So this equation is correct, right? 4x1 plus 4 here.
Will this kind of questions come in exam?
Okay. Yeah, I can expect such kind of questions, but not such a difficult computation. In exam, we will ask some easy to read solution.
Yeah, because otherwise will end up doing only one question.
Yeah, correct. Yeah, I agree. And so we'll not have some. So we can easily figure it out the way, right? Okay, using these four cases alone. Try to do it quickly so that you reach this optimal solution. Okay, so let me verify this answer and then I will post in Discourse. Okay.
Okay.
Yeah, sure. Okay, so how was the session? Just a feedback on how the session was, and then if you want to have any doubts, that also you can type. Some concept-wise understanding.
Very interesting, very nice. Understood everything.
Okay, thank you.
Ma'am, I have a doubt. In the tutorial, they were taught something about primal and dual solution possibilities. There was that is. I didn't quite understand that. So that could be explained, because what is finite, optimal, and feasible? What's the difference between the two?
Oh, okay, fine. So let me open that presentation. So let me stop sharing this SWI and then open that. This one only you are asking, right? Types of solution person.
No, ma'am. This is that was a grid between primal and dual. It's towards the end, I think.
It's the conditions, ma'am. Even I didn't understand that.
In this Kkt, I have a question that in the whole Kkt, we are just doing four conditions and we are solving that.
Yes, correct.
Is it?
That is enough. One way of initially what we can see, this is for example from this tutorial problem. So if you consider here in this here I would have showed you that approach that U1 and considering that approach. Because straightforwardly, what you do is only after reaching this complementary slackness condition, you try to solve from this equation itself, whether it is giving the optimal solution or not. So this is somewhat time-taking process because you need to verify, you need to jump in between equations, and then you will not get some concrete steps to finally reach the answer. Since this is a simple problem, I have shown you this way. But in case if we have more number of constraints or something like that, it is always good to follow in a streamlined approach. So that is why I am giving you that 4 cases, because these are the
Okay,
four
okay. So,
cases. Apart from that, no other cases will be there to solve. So that is easy to try.
okay, okay. So to easily solve it, we are using the U1, U1, U2 equal to 0 or not equal to 0.
Yeah.
That
So basically, from this, that method is basically directly obtained from this complementary slackness condition only, because this KKT is solvable only by looking at this complementary slackness condition, because we do not have a starting point to solve all these equations, because these are not simple linear equations to solve in given 2 equations, find the value of 2 variables and all. So this problem consists of so many equations, right? So you have, if you see here, there are 4 equations, but 4 different variables. So if there is one more condition, then there will be more than 5 equations with only 4 conditions. So at that time, you will be stuck with from where do I start? So this way you can concretely start working on the problem. So that is why I introduced this method. That is
yes,
substituting
yes.
this.
Got it. Thank you.
So you're talking about this. This
Yeah,
one.
this one.
This one, right?
Yes, ma'am. This one.
Okay, okay. See here, finite optimal in the sense the value that is in the boundary region. For example, see here.
So that's the feasible region only. No?
Feasible. See here, if you consider here, this is the feasible region, the entire feasible region.
Right.
Finite optimal in the sense this one lying in this, we have this boundary, right? Optimal values that sticks to this constraints.
Right.
That is not only the feasible. A feasible consists of this whole set.
Okay. Okay. So we are talking about these 5 points are the finite optimal.
Right. Yeah.
Okay.
Yeah, that is why that condition.
Then the conditions also, how did we get at this?
On this
I mean,
table.
why is this impossible? And I couldn't understand this table because
okay.
some of them are clear because you're saying feasible for dual and feasible for primal is possible.
The possibility is clear.
Yeah. The possibility is not clear. How did you arrive at that?
Oh, okay, fine. See, this under a tip from reference only. See, for example, the impossible case, let us consider. See, for example, in the dual problem, if it is finite optimal, and then if the primal is unbounded, this is how you relate this table. You just don't see the answers like possible and impossible. How do you inference from this table is, if the dual solution is finite optimal, and if the primal solution is unbounded, at that time it is impossible to have such a solution.
Okay.
Yeah, so that is how you read from this table.
Okay.
And you can also read otherwise. So if the primal solution is left unbounded, if this primal is unbounded and the dual is finite optimal, such kind of solutions don't exist. That is
so
impossible.
how's the last one should be possible? Because if the primal is feasible and the
Primal
dual
is
is
feasible.
dual is finite optimal, then it should be possible.
Here.
Yeah, yes.
But it is impossible only if the primal is feasible and the dual is finite optimal.
Fine. This is not clear to me.
Oh, okay, fine. So there is some misunderstanding, I think. When the solution feasibility, then the dual should also be feasible. Okay, let me check and then post, okay, in the discourse.
Yes, ma'am.
This condition, yeah.
Right.
I
And
hope it should be
feasibility actually
possible,
means
right?
that two different constraint equations meet at some point and they are unbounded. That is what feasibility means, right?
Yeah, that is what they're bounded.
They're bounded also.
I think feasibility, what you said was the region.
The
Where
region,
they are
it's region,
bounded.
yeah.
Where all these constraints meet.
Yeah.
Yeah.
So out of
But
them,
they don't need to be bounded, right, ma'am? They can be unbounded.
The feasible region can be unbounded. That is what in your example that we saw, right?
Yeah, yes, ma'am.
But in a bounded region, you can have optimality only at those points where they cross the
in the bounded region. Yeah, correct.
Wherever
So
that will be the only optimal points. Right.
Okay.
That is clear, ma'am. But this last one can be posted.
Correct. Yeah, I will also check and then I will do it back. Okay.
Yes,
I'll
ma'am.
definitely solve this and then I will post a new topic based on this solution.
Yeah. Thank you, ma'am.
Okay. So, any other doubts in this week 9?
Ma'am, actually, I'm finding like doing things difficult in this week. Can you suggest me some more practice problem from where I can practice?
More practice problems for which topic you need for this?
For week 9, optimization.
Oh, I see. See, in our portal, right, you have this books for convex optimization and all. I think in those books you can find some extra exercises.
Ma'am, I opened the book, like it is too huge, finding things which were taught by sir, like because in optimization, sir, I've taken only very limited things.
Oh, Abhishek, you are okay. Yeah, Abhishek, I think some other website references only other than that are with some solved examples. So the standard book is Boyd and Vanderlei book. That is why I referred to you that because we mostly stick to that standard references. I will also share then some of my other references to the same thread I will share. Okay.
Even it is like very good if you share at least some more problems, solve problems, kind of a link which basically lead us to the problems which are lead to the good source and it is also reliable.
Oh yeah, fine. I will just website because Princeton University, right? So in Princeton, from Princeton University, there are a lot of technical details similar to our content in this optimization. So you may find many Princeton University reference. I will share it in that thread itself.
Okay.
That is a website reference I have. From there, you can find the lecture material and also some solved examples. Otherwise, this optimization theory, this itself is a huge subject actually.
Actually, from the beginning and like from the starting of this course, like the only thing which is I feel is where I lacking or maybe other people are lacking is like practice problems are not enough because
you need more practice problems.
Yeah, basically we need more practice. Because I'm not comparing, but we had a statistics course, and content was difficult over there also. But the way they have created the practice questions and tutorials, it was like very good. Like they have increased the number of practice questions for us. Okay, so
fine.
Those things will like by doing those things, we basically gain the confidence in that particular subject. But here we are lacking in that thing.
Okay, see, I agree with that, but see, when you come to machine learning techniques, machine learning foundations course, right? Some basics on linear algebra weeks, right? See, it is also similar to that of what you have studied in mathematics. So that is why we didn't go on with the many problem solving there. And in later weeks, it is difficult to solve hand code all the numerical problems. So that was also one of the issues. We find those problems which are easy for you to solve. Otherwise, we can do coding itself directly. If you increase the number of problems, how we can do it? We can increase the number of data points and all, and some mathematical operations. So that way we found difficult for improving the number of problems so that it may be some heavy computation wise. So that is the reason why we stick to some minimal number of problems in the tutorial as well. But sure, we will take this feedback to the team, and then let's try to add some more problems, some additional exercises.
Yeah, thank you so much, ma'am.
Sure. Yeah, thank you for your feedback. Yeah.
Thank you.
Okay. So if you have no more doubts, then shall we close the session?
Yes, ma'am.
Okay.
Sure,
Okay,
ma'am. Thank you.
Yeah, okay. Thank you all of you for participating in the session. Have a nice
Thank you,
weekend.
ma'am.
Thank you,
Yeah.
ma'am.
Thank you. Thank you, all of you. Hello, Vignesh, you can close the session. The session is over, so kindly close the session.